Hello, we are going to be looking at approximating the area under the curve by adding up rectangles areas. And then we're going to be using calculus to do that more exactly. It's very important to find the area under curves. If you've ever taken any kind of statistics class or studied the normal distribution, you know that that's all about finding the area under the curve. So we need to know how to do this. It is extremely important. This is from the GeoGebra website, and I just wanted to show you what's going on. We're going to be working with the function 1/2 x squared, and we're approximating the area under this curve from x equals 2 to x equals 4. And we're going to try it with two rectangles first. And you can see if we only use two rectangles, there's this big area above the curve that's going to be extra. So we're going to overestimate by a huge amount when we do that. We can increase the number of rectangles to 4, and we're going to be doing the longhand. And then that area that we're overestimating by goes down. So it's not quite as large. It's still pretty far off the actual area under that curve. As we increase the number of rectangles, that extra area goes down and our approximation gets better and better and better. So we end up with, if we get to just a really skinny rectangles, get to 100 rectangles, we're pretty close to an approximation. So if we did 1,000 rectangles, we'd be even better off. It'd be pretty hard to draw that, but you could do it. So what we're doing at the end of this is taking the limit as the number of rectangles goes to infinity, and then we'll get the actual area under the curve when we do that. We want to also discuss the left-hand endpoints and the right-hand endpoints. She'll be dealing with that. You can also do midpoints of the rectangles, but we're not going to be working on that. We'll just do the right hand and left hand. Right-handed means the height of the rectangle is on the right side of the rectangle where it hits that curve. So then you draw your rectangles, you go to where the curve is and draw the rectangle out to the left of that. So left-handed endpoints is the opposite thing. Let me get fewer rectangles here so you can see better. So then the rectangle is hitting the curve on the left side of the rectangle. So right rectangles, the rectangle is hitting the curve on the right end of the rectangle. Left rectangle, it's hitting on the left side. So we're going to be using area of a rectangle is length times width, and we'll figure out, approximate how much area is under the curve that way. So here's a picture of our curve, 1/2 x squared. Between 2 and 4, and we've split it into two rectangles. So because we have two rectangles, the width of each rectangle is going to be 1, and the height is going to be the function value at the right end point where we've drawn the rectangle. So to draw these rectangles, what you do is you look at how many you're supposed to have. We're supposed to have 2, so we're going to split 2 to 4.5 and draw the line at 3 because that's exactly the center between those two. And then we're just going to draw that line straight up, and where it hits the function, the pink line, that's where we're going to draw our right-handed rectangle. If we were drawing left-handed rectangles, they would be very short, but these are right-handed, so we're going to overestimate with these right-handed rectangles. So the width is 1, the height is the function value at those purple dots. So we put that function value in to get the height of the rectangles. We multiply the height times the width to get the area of a rectangle. And then we add those two rectangle areas together to get an approximation, which is 12.5. And we know that that's too big because we can see those big areas above the pink line inside the rectangles that we're overestimating by. Okay, we're going to try again with 4 rectangles this time. The same curve, we're just splitting it up into rectangles that are half the width of the previous one. So this time each rectangle is 1/2 wide. So we're going to change that. And then we still have the same places where we're going to put the height in for the rectangles. So each area is the width times the height. And we find out the areas of each of the 4 rectangles, add them together, we get 10.87. That's significantly smaller than our previous estimation, but we can still see that we're overestimating by a fair amount. So what we want to do then is to go ahead and use some calculus on this. And here is what that looks like. We're going to find the actual area under the curve, no more estimating. And we're going to do that by using limits. So we're going to take the limit as the number of rectangles goes to infinity. And then this big capital Greek letter sigma stands for the sum. And those ends are the rectangles. So the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. We're doing the same thing. We just have an infinite number of rectangles. That means that the width of those rectangles is infinitesimally small. So that's what that delta x is. That delta x means the width of the rectangle. And as the limit, as the number of rectangles goes to infinity, that thing goes to 0. It doesn't actually hit 0. You still have a rectangle, but it's so close to 0 that it might as well be 0. So that's what we're doing here with our summation. So if we rewrite that using our integral floof, that's not the technical word, by the way. It doesn't really have a good name. That means sum. That floof is standing in for the limit and the sum part of the previous equation. So that's the limit and the sum together. And then we have f of x, which is 1/2 x squared in this case. That's the height. And dx takes the place of the width. So that delta x becomes dx. And we can go ahead and take that integral. This is a definite integral because we're going from 2 to 4. We have a separate video on how to do that. But when we do that, we find that the actual area underneath that curve is 9.33. So by changing the number of rectangles, we've gone from over 12 to 9.33 as the actual. And that's what integration is all about. So good foundational piece here. And that's it. Thank you.